Welcome to part 2 of building the obstacle avoidance drone. In this video, I will be completing tasks 1 and 2, fixing the soldering and controlling the drone with a joystick respectively. I used many sources for task 2, and the codes that I wrote are influenced by a very good tutorial on howtomechatronics.com. I have added all the sources in the description of this video. Let's start with the soldering. I removed the damaged cable first. Next, I tinned the contacts. Then I tinned the wire. Next, I soldered the wire that powers the Arduino. Finally, I soldered the battery wire to the switch. To test that the soldering had worked, I have wired up the H-bridge and the Arduino. We can see that the soldering has worked as the LEDs on the Arduino and the H-bridge modules are lit up. With task 1 completed, we can now start task 2. Experiment 1, controlling one motor. In this first experiment, I will be attempting to control one of the motors through a H-bridge. The goal of the experiment is to have the motor run in two directions. DC current is where the electricity flows in one direction, going from negative to positive. When I attach the positive lead to one terminal of the motor and the negative lead to the other, the motor will then run in a clockwise direction. However, to get the motor to run counterclockwise, I would need to flip the position of the negative and positive leads. This is not a useful method of changing directions. Imagine having to change the motor wires in a Tesla every time you wanted to reverse. It is not efficient nor safe when using a high current circuit. This is where the H-bridge comes in. The H-bridge is a simple circuit that allows a motor to run forwards or backwards. In this circuit diagram, we see a simple H-bridge which uses 4 switches: S1, S2, S3, S4, in such a configuration that resembles a capitalized H. I have recreated the H-bridge circuit with a breadboard. The orange wire represents S1, the white S2, the green S3, and blue S4. When S1 and S4 are turned on, the motor will turn clockwise. If I turn on S2 and S3, the motor will turn counterclockwise. Experiment 1 is a success, as I have been able to create a simple H-bridge and change the direction of rotation. Experiment 2, controlling the speed and direction of one motor. The second experiment will take what we learned from experiment 1 and use a smarter H-bridge which can be controlled by an Arduino. The L298n is a more advanced dual motor H-bridge. I can control 2 motors at the same time and have them run at different speeds with this unit. This is the logic diagram of the L298n. It looks very daunting at first, but it works in the same way as the switch H-bridge. To drive the motor clockwise, we set the enable A and the input 1 pin to high and the input 2 pin to low, which outputs to output 1. This is the same as having S1 and S4 closed in the switch H-bridge. For counterclockwise movement, we set enable A and the input 2 pin to high and the input 1 pin to low with outputs to the output 2. What if enable A is set to low? Then both output 1 and output 2 are set to low, meaning that nothing happens. What does the enable pin do then? The enable pin controls the speed of the motors by using pulse width modulation, or PWM. PWM allows us to change the average value of voltage supplied by changing the frequency at which an electrical signal is turned on and off. The fraction at which the signal is on compared to off in one period is called a duty cycle. If a power supply has a maximum voltage of 10 volts with a duty cycle of 25%, the average voltage will be 2.5 volts. Similarly, if the duty cycle is 75%, the average voltage will be 7.5 volts. I can use a potentiometer to change the value of the duty cycle, which will change the speed of a motor. I can also use a button to switch the direction of rotation. This is the circuit diagram for the second experiment. I am wiring up the circuit here. Let's look at the code next. This is the code for the experiment. This may look similar to C or C++, and this is because Arduino is coded in C. At the start of the code, I define each digital pin. I also define the constant for the button being pressed and initialize it to false. In the setup, I have set the pin modes for each variable. The enable in 1 pin and in 2 pin are outputs as they send the signal to the L298n. The button pin is set to input as it is used for controlling the rotation direction. In the loop, I start by creating the code which allows the Arduino to read the potentiometer. The Arduino has an analog to digital converter with a resolution of 10 bits. That means the Arduino can only read integer values between 0 to 1023 on any analog pin. That means the potentiometer has a max integer value of 1023 and a minimum value of 0. The map function allows me to map the potentiometer to any range. In this case, I have mapped the potentiometer to an 8-bit range, 0 to 255. The reason for using an 8-bit range is not arbitrary, as the Arduino can only output PWM signals at 8 bits. The analog write function allows me to output the potentiometer value to the H-bridge through the enable pin. Through this, I can change the speed of the motor. When the button is pressed, the variable pressed goes from false to true. If pressed is true, then the motor will run forwards by setting the in1 pin to low and the in2 pin to high. If pressed is false, then the motor will run backwards as the in1 pin and in2 pin values are switched. So let's test this code by turning on the drone. Nothing is happening. The problem is not with the motors nor the batteries, as we saw that they were working in experiment 1. When I rewired the power unit into the 12-volt input, the L298n unit's LED doesn't appear to turn on. When trying to diagnose the problem, I found that the capacitor hasn't been soldered correctly. The wire that should be coming through is missing. After soldering the capacitor, the unit's LED is not lit up. Let's try with a new L298n unit. With the new unit wired up, we can see that the motor is still not running. By using a multimeter, we can see that the total voltage of the 4 batteries is not 6 volts, but 4.95. We can see the voltages of the batteries. These are lower than the 1.5 volts rated output when new. With fresh batteries, I now have a voltage output of 5.93 volts. When measuring voltage across the motors, I saw that the voltage had dropped to 4.05 volts. That is a 2 volt drop, which is consistent with what I found online. The original L298n also works with the fresh batteries. Now, with enough power, I can change the speed of the motors and with the press of a button, change the direction of rotation. We have reached the final experiment for this video and the second task, controlling the drone with a joystick. A joystick contains 2 potentiometers, one acting in the X direction and the other in the Y direction, along with a push button. When the joystick is in the center position, the potentiometer value is 512. The max value will be 1023 and the minimum value will be 0. To move the drone forwards, I can set it so that if the X position is greater than 512, the drone will move forwards, and if the X position is less than 512, then it will move backwards. To turn the drone, the motors will need to be turning in the opposite directions. To turn right, the left motor needs to move forwards and the right motor needs to turn backwards. I can set the drone to turn right if the Y position is greater than 512. If the Y position is less than 512, the drone will turn left. This is the circuit diagram for the experiment. It is a lot simpler than the previous experiment. With the circuit wired up, let's look at the code. This is the code for this experiment. I once again define all the digital pins. I also initialize the speed of the 2 motors. In the setup, I set all the pins to be outputs by using pin mode. There are a number of things that are happening in the loop section. I have the Arduino read the values of the X-axis and Y-axis of the joystick. Each condition relates to the direction in which I push the joystick. If I move the joystick forward in the Y-axis, the drone will turn right. If I move the joystick backwards in the Y direction, the drone will turn left. If I move the joystick forwards in the X-axis, the drone will move forwards. If I move the joystick backwards in the X-axis, the drone will move backwards. The final condition is if I don't move the joystick, the motor will not turn. The analog right at the end is to set the speed of both motors based on the position of the joystick. The further I move the joystick from the center position, the faster the motors will run. I can control the drone with the joystick. It can move forwards, backwards, turn left, and turn right. This is the end of part 2. I have completed both tasks 1 and 2. I have also learned how to control the motors with the H-bridge and have been able to successfully diagnose a fault in the system. Stay tuned for part 3, where the drone will start to see obstacles in its path.